class? They're basically just long metal tubes that contain a ricocheting of electromagnetic waves. That's all they are. So, that said, what I'd like to do, and I think this is where I left off.
Oh,
I'm going to go through the TEM and TE modes of the waveguides. And the way I'm going to do this is try to put a special emphasis on things you need to be attentive to that really are important and not really worry about some of the things like spurious modes and stuff like this. So anyway, when we talk about waveguides, in general, we're going to start talking about rectangular boxes that are infinitely long. And this will be on the x-axis, have a dimension A. This will be in the y-axis and have a dimension B. When you look at this, if that's x, y, z is coming out of the board, and all it is a rectangular box like this. Y'all with me on this box? Nothing special about this. But the thing about that rectangular box is the electromagnetic fields tangent to those walls are zero. Y'all with me? Now that's real important. So if you had an electromagnetic, if this was a perfect conductor, like that box is going to be, the metal box is going to assume perfect conducting walls, there can be no tangent electric field. Y'all follow me? At this point, the tangent field would be zero, but the reflected field would be equal and opposite to the incident field. So if an incident field is 1 volt per meter, it would create an electric field that would be in the opposite direction of -1 volt per meter, and it would create it in a way such that it exactly cancels that. Y'all with me? It shorts it out. That's real important. So when we look at this, I think I did this last time. I start the wave equation, and I developed the del squared equation. This is, y'all remember this class? You don't? Well, in a nutshell, you don't need to write this down. If I take curl of H, and here we're going to assume that sigma is 0, because inside a waveguide, if you got a non-zero sigma, then why are you doing it? It's supposed to propagate electromagnetic energy. If sigma is non-zero, then it's going to short it out. Y'all follow me, class? It would defeat the purpose. We assume sigma is 0. We assume it's lossless. So this would be equal to curl H is normally sigma E plus J omega epsilon. This will be J omega epsilon times E. And then when we have curl of E here, that's minus J omega U times H. These are the two Maxwell's equations of sigma 0 and when the frequency range. With me, everyone? Now, the next thing I'm going to do is create just one equation with one unknown. I'll take curl, and you'll see this over and over again here. Curl of E is equal to minus J omega mu times curl of H. And where do I get curl of H from, class? Very first equation, right? And just plug it in. So now I have J omega epsilon E. And this is in the phasor domain, by the way. So now, and I've done this before. I don't mean to hurry so fast, but we've done this several times. I'm just trying to get to the real interesting part. So now the next thing I do here is that standard definition where I can say curl of E is really gradient divergence of E minus del squared of E is equal to, and here I have J times J, which is -1 with a minus is +1, right? And then I have omega squared mu epsilon here times E. I'm kind of curious about this. Does anybody remember my next step here? There's one thing I'm going to do that has something to do with this. Anybody?
You can get rid of the gradient.
Can you see it back there? You were squinting. Can you see it okay? All right. Yeah. How come I can get rid of this? What am I going to assume? Divergence of V is equal to rho V is 0, right? I'm going to assume it's charge-free also inside the guide. This is going to be in the dielectric region. And that means divergence of E, which is rho V over epsilon, will be 0 as well. So I get rid of this. That's my point. Y'all remember doing that now? Admittedly, I don't, but I'm trying to get there. Now, at this point, we got one equation, one unknown. We'll get everything to one side, and we get this. We have del squared of E, right? Then I have plus omega squared mu epsilon, right? E. And obviously when the phasor domain is equal to 0, that's the equation we use. Now I'm going to tell you about the del squared operator. This is a vector del squared that Dr. Whitmer's book doesn't have. In the back of your books, on the last page, you're going to see the Laplacian. Y'all see that? Very last page. It's a del squared operator. I'm going to talk about how this relates to this particular problem. But I do want to say, in general, the del squared operation for cylindrical and spherical is much different than the one I'm showing you for Cartesian. So, just a brief side note. When I have del squared of a scalar quantity, I'm going to just use E z, because that's the one I'm going to do. Second derivative of Ez with respect to x squared plus second derivative of Ez with respect to y squared plus second derivative of Ez with respect to Ez squared. But that's just del squared of Ez. Y'all follow me? Now technically, if you have, would you do me a favor and not write this down, just listen. This is not going to be something I'm going to quiz you on, but I want you to have an appreciation for this. So just listen. When you have del squared of a vector quantity, and we'll do this in Cartesian, E in general has x, y, and z components possible, right? Y'all with me on that? It doesn't have, it's not a scalar, it has vector quantities, so there's an x, y, and z. This really is, if it's in Cartesian, del squared, right here, of the x variable in the ax direction, plus del squared here of ey in the ay direction, plus del squared of ez in the az direction. Now, if you think about this logically, each one of these del squared operators has three derivative, it's second derivative terms, right? So if you did this, in general, you would have 9 derivative operators there, in 3 in x, 3 in y, and 3 in z. You all see that? That is a monster. All right, we're not going to do that. We're not that stupid. All right, what we're going to do is reduce this to something meaningful to get an answer that's useful in our analysis. Do y'all follow me? So here's what we're going to do. Now this is absolutely true, what I just put up. What we're going to say is, when I talk about waveguides, z will be the direction that the propagation will occur in. So these will be very long tubes laid out in the z direction with cross section A by B, all right? And they're perfect conducting edges. The wave will ricochet around in there. And there's 2 types of wave that we talk about inside those waveguides. Do you remember what a TE wave was? It was what? It was one where the electric field was transverse to the plane that it went into, or at the interface, it was exactly flush with the interface between media 1 and media 2. Y'all remember that? When we talk about electromagnetic propagation in the waveguide, if you listen to this, if we have a TE wave, the electric field will be in the x or y direction, but no z component. The wave will just ricochet like that, but the E field will not have a component in the actual z direction. Do y'all understand that? Now when you talk about TM propagation, you all understand, transverse magnetic. It means the magnetic field will be in the y or x direction, but there will be no z component. Do y'all follow me in that class? So what we're going to do in his book, the way he does it, he talks about TM propagation, and here's where it gets a little bit confusing. So in his book, if you look on page 388, he starts with the TM mode, and that's where I'm going to start. So right here, I'm going to take this, and I'm going to talk about the TM mode of propagation, and that means no HZ. Okay, because HZ will be, the Z will be the direction of propagation. Y'all follow me on that? This is, yeah.
Because in a waveguide, do you have TE and TM, or is it always one or the other?
That's a great point. You can superimpose modes. The real truth with waveguides, rectangular guides, they work almost always in only one mode. And that's going to be the 1-0 mode. All right? I'm just telling you this, it'll be equal to the TE10, but I can't get there. So what we want to do, and here's why. Just because that's a question should have approached. You can have both modes. The question is, why would you want both modes? You'll see in a bit that they propagate at different velocities, and how would the energy or power be distributed between two modes? So you have one propagating at one frequency and another at another, the same frequency but a different mode. The energy and power would move at different velocities. The way is this. Remember I said that these are high frequency filters, that you have to be above a certain frequency before anything will go down that pipe. Do y'all remember that? We go just over the lowest frequency that's allowed, and it happens to be the TE mode. And it will allow all the energy to propagate in only one mode, and you won't develop the second or third, any other modes. So yes, you can have it. The truth is, we arrange things so we don't. All right, that's something that comes down the road, but that's the real thing, all right? So anyway, for this, no HZ, we only have EZ. Y'all follow me? Now we say, well, we're allowed to have an EZ. So this equation, take a look at this for a second. I want to do this good this time. Now I'm going to slow down. Y'all with me how I got there, right? Now we're only looking at the EZ mode. We're only looking at EZ. You realize that the del squared operator would have a del squared of the EX and a del squared of the EY, but their direction would be an AX and AY. Y'all with me? So vectorially, this is really just AZ. And when we do this equation, and I'm going to write it down, this del squared operator, if we only care about the Z component, or the AZ component, then we get the second derivative of EZ with respect to x squared plus the second derivative of EY with respect to y squared plus the second derivative of EZ with respect to z squared plus omega squared mu epsilon times EZ equals 0. Now here's what I've done. I've removed all the other complexities. I'm focusing on only the z component. Remember, each one of these differential equations in the x, y, and z direction will have solutions that have to be mutually consistent. If you get it here, it still works for the other ones, okay? If you don't appreciate that fully, you will in time, all right? But this is going to be the equation we're going to look at, all right? And this is for the TM mode because there's no magnetic field in the direction of propagation. Everybody got that? Yeah.
In the numerator there, those are all
These are
second
double
derivative
derivatives
of
of
EZ.
EZ. Oh, I'm sorry. That's supposed to be a Z. I apologize for that. They're all derivatives with respect to EZ, either X, Y, or Z derivatives. They're double derivatives, okay? Now, when you get down to this point, I'm going to make some changes to help keep the books. Do you see this omega squared mu epsilon? Isn't that really beta for a lossless case, right? Remember, if you have a lossless wave, gamma is equal to alpha plus j beta. Alpha is 0 if it's lossless, right? And then you get the square root of j omega mu times j omega epsilon, or really j omega squared mu epsilon. Y'all with me? All right. What we do is call this right here, and I'm being consistent with Wentworth's book, this is beta unguided squared. And I just make a notation, this is beta unguided is omega times square root of mu epsilon. You with me? Now, so I changed one thing there to simplify. Now we do something called separation of variables. And I'm trying to do this efficiently. I'm going to remember separation of variables when you had differential equations. One, what was the power of that? You assumed that you could take something where you have derivatives of x, y, and z and create a function that's just the function of x, just the function of y, just the function of z. And when you did the derivatives, you could separate out, right? All the things that have to do with x, all the things have to do with y and z. If you don't remember it, you're about to see the power of that. So in separation of variables, and I'll do it here, what we do, maybe I'll do it here, we assume something. By the way, am I too far over for the camera or not?
No, you're good.
All right, what we do is this. We assume that EZ is just the function of x. And the way Whitworth's book does it is like this. Just the function of y and just the function of z. It could be like sine of 10x plus or times cosine of 3y times e to the minus 10z. Do y'all follow me? There's some separable functions. When we do that and plug that in here, if you remember separation of variables, this is the power. When I take a double derivative of EZ, it's a function x, y, and z, with respect to x squared, I get two derivatives on x, but the y and z remain unchanged, right? So here's what happens. This becomes x double prime yz. Now, I'm simply omitting the argument of small x, small y, and small z, just to keep the books a little easier. Do y'all see this? All right. Plus, this will become x, y double prime times z, plus, and this will be x, y, z double prime, plus beta unguided squared times x, y, z equals 0. Now, what I'm saying when I have like x double prime, that's the second derivative of the function x with respect to x squared. Y'all follow me on that? Y'all familiar with those primes, right? Being derivatives? One prime, one derivative, double prime, double derivative. With me? And this is real standard stuff. Now I get down to here, y'all see how I got there? Right? Now what I'm going to do is this. I'm going to divide the entire equation on both sides by just the function x, y, and z. Now here's the reason, just listen. You see how I'm going to get x double prime over x, and the y and z go away. I get y double prime over y, and the x and z go away. And I get what? Z double prime over z, and the xy, and then I just get beta unguided squared. Do y'all follow me? So I'm going to put that up here. Actually, I may put it over there, give myself a little more boardroom. All right, so when I do that, I have x double prime, or yeah, I just put it up here. X double prime over x plus y double prime over y plus z double prime over z plus beta unguided squared equals 0. Now I'm just repeating what I said. Y'all with me? Please be attentive here. You have to see what happens next to appreciate it. And I want to say one other thing. I don't ask questions for you to prove or show that a certain equation comes from the two Maxwell's equations. Do y'all hear me on this one? Now, Adele Shearer or somebody else, Riggs, might ask that in this class. In physics, you get that. In math, they'll ask for proofs, or they'll ask you to develop. In engineering, it's my own opinion. I want to make sure you know how to do it if you had to, but we're going to apply the results. And I say this because I'm going to get questions about this every single time, because there's a homework problem that says, using the first two Maxwell's equations, come up with this and show me the general solution. That's not going to happen on a test. That's the last time I say it. Please, you share that with your friends if they ask for a good word. So from here, I'm going to make this comment, and you have to appreciate it. You see how this is just a function of x, right? Now listen. So it'd be like f of x here. You don't write this down, just listen. This is like some g of y, just the function of y. It could be sine of 10y, it could be anything, right? Plus, this is just the function of z. plus, and this is a constant, really, right? Y'all follow me? Now that has to be true for any possible value of x, y, or z. Y'all follow me? And the only way that's true for any possible value of x, y, or z is if each one of these terms is a constant. Do y'all see that? If they're equal to a constant, then that will work. And the constants will be such that when they're added to beta unguided squared, you get 0. Y'all follow me in that? So, if you don't fully appreciate, hang on. Hopefully you will. So now I'm just going to get rid of this little statement, and I'm going to put down what Whitworth has in his book. I don't like his symbol selection, but that's okay. This he's going to call minus beta x squared. Usually in other books that would be a minus k sub x squared. K is usually the wave number. I'm just telling you. Here, this will be minus beta y squared. Whitworth's book doesn't have a beta z. He just has beta, because beta has to do with the direction of propagation. I'm going to put a beta z down here. Minus beta z squared plus beta unguided squared equals 0. And make a note, Whitworth's book has his beta equal to my beta z. The reason I put that beta sub z in there, if you look at any other textbook, it will usually have something either k sub z or beta sub z. And this has to do with the wave number in the direction of propagation. That becomes very important. Y'all with me? Now, when I go from here, right? This is that is that is that. So now, y'all see what I'm doing here? I'm just showing you how they equal a constant. When I take a look at just the x component, I have this x double prime over x, right, is equal to minus beta x squared. Y'all with me? Here's where the magic happens, kind of. Nothing fancy here, nothing new. All right, that's a double derivative, right? So it's second derivative of x with respect to x squared, and it's divided by the functional form of x is equal to minus beta x squared, right? And here I've just replaced the prime, double prime, with the actual defined derivative, right? Now I multiply both sides by the functional form of x, and then I set it equal to 0. This is exactly how he does it in his book. This is the key. Y'all see that? That's a homogeneous differential equation of second order, right? Or second order homogeneous equation. These are things in time you'll know like the back of your hand, the solutions to. We could solve it using Laplace transforms. We could do separation of it. We could do a lot of things. I'm just going to get to the bottom line in this one. You remember how to use Laplace transforms, right? You could do this instead of time, use space as the variable you're doing Laplace with respect to. You can solve it. I'm not even going to bother with that. I'm going to go up here and show you something. When all is said and done, the solution to this are going to be x of x. It's going to be some function, and just call it, you can call it E naught for lack of a better term, and it's going to be some function, and it could be times a cosine of beta x times x plus some, I'll call this, tell you what, I'm going to just call this a, plus some b times the sine of beta x times x. Really, if you go ahead, if you use cosine of beta x times x, take two derivatives of a cosine, you get beta x squared out in front, and then you get the cosine again, right, with a negative sign. Isn't that right? Think about that. So you would have minus beta x squared cosine of beta x times x. Then you would have beta x squared times the cosine. It goes to 0. Do y'all follow me? In other words, these are solutions to this differential equation. Do y'all follow me on this, class? Give me a show of hands if you do. Now, if you don't just gravitate and love this stuff, don't worry. You're not the first that didn't like it. You want to see it applied, but you have to appreciate this. You have to understand what's going on here in order to really move forward with this stuff. So that's the equation, and remember, the E field itself is in the z direction, and it's a function of just x of x, just y of y, and just z of z, right? And here's where we use boundary conditions to eliminate any kind of solutions that are disallowed. What I'm really saying is this x function, whatever function we choose for x, it has to meet the boundary conditions that would be true for EZ. Does that make sense? Forget about the y and z for now. Just think about x. Well, what are they? Well, for the waveguide, let me redraw this. If this was the x direction and this is the y direction, right? Remember, this is the origin. This distance is A, and this distance is B, isn't it, class? Y'all remember that? Now, what are the boundary conditions? EZ has to be 0 when x is 0. This is a function of x. You with me on that? And it has to be 0 when x is A. Do you all see that, class? Everybody see that? Think about it. EZ is going to be, that's tangent to the boundary. And it has to be 0 when x is 0. And it has to be 0 when x is A, doesn't it? Now look here. If we examine the cosine variation, well, cosine, when x is 0, cosine is always going to be a value of 1. Do you all see that? That can't work, and it doesn't. The only possible solution is this. All right? So, and I know this gets a little bit disconcerting, it seems too abstract, but this is how we determine the allowable mathematical solutions, and this is going to give rise to a whole lot of information in a second. So that means when I take a look at the x variation, it will only be this. Matter of fact, let me do it this way. X will only have a function that'll be likened to simply the sine of beta x times x. But now, how do we get the value for beta x? Remember, this is going to be, I could make it equal to it exactly and put a constant here, right? If you want me to, but that's proportional to. All right, now look here. Where else is it 0? Didn't I say it's 0 here when x is A? Y'all follow me? This is real important. So that means the sine of beta x times A has got to be 0. When is sine 0? As far as its internal arguments anyway? Sine of 0, 0, right? Sine of pi, sine of 2 pi, sine of n pi. You agree with that? Right? So now I can say that beta x here times A is really, has to be equal to n pi to meet that boundary, second boundary condition. Do you agree with me, class? All right, keep going on this one. What does that make beta x? It makes it n pi over A. All right, so now we actually have the constant that goes inside that sine x. All right? You'll see why this is important in time, but just trust me, you have to go through the mathematics to get all this information. This will give us velocity, give us a whole lot of stuff in big. That's beta x. Now, if we do the same thing, and you don't have to write this down, just appreciate what I'm saying. Remember, that was this equals this, right? This one will be minus beta y. You all agree with that? All right? So don't write it down, just listen. Now I do the same thing, only now this becomes y, and these two become y double prime over y, and then this is going to be, basically it's going to be the same exact thing, only with y, right? And it will lead to this, where this will become, I'll rewrite the whole thing. It will be just the second derivative of the functional form of y with respect to y squared plus beta y squared y equals 0. I know a lot of people don't really appreciate this until they have time to think about it and see how it's applied, but we're getting a whole lot of information out of this, trust me on this one. So now, that has the same exact form as the last one, right? Now remember, it could be a sine, it could be a cosine. Do you all remember that? How did we determine it was a sine?
Where is the zero?
We looked if it could be 0 at x equals 0, right? The sine fulfills that automatically, doesn't it? And by the same token, we'll find that y, the y function, will be equal to some constant times the sine of beta y times y. How do you think I find out what beta y is? Anyone?
Same way.
Say again?
The same way you did the other one?
Exactly what is it? The boundary condition, right? Only now it's not at x equals a, it's at y equal b. Y'all hear me on that? Everybody? It's exactly the same way. So when I do this, when I do it, I would say that, and I'll just put it here, sine of beta y times a equals 0, and therefore beta y times a is n, or m, pardon me. Maybe, did I use n there? I'll tell you what, I can make this m because I did this first, and make that n because it comes afterwards. But you all follow me, these are two different symbols. They're integer values. Whenever you see m and k, they can have integer values, 0, 1, 2, 3, 4. They can't have 1.257. You all follow me on this, class? All right. That means beta y is equal to n pi over, and that should be b, but that's on me, over b. Good with that? With me? Now, you're going to say, well, what about the z business here? Here's the thing. For the z thing, and I'm not sure the best way to explain this, but I'm going to just tell you what happens here. When I have the second derivative of z double prime with respect to z, right? It's going to be that plus beta z squared times z equals 0 right here. It's true, z could be a function, it could be cosine, it could be sine. Do y'all follow me? But the thing I failed to say in the previous one, because it's a solution that's errant, is it could also have an exponential form. So the functional form of z will be some constant, now you c, and it can be e plus or minus j beta z times z. Do y'all follow me? Now the reason I'm saying that, think about what actually binds the functions or the solution in z. Well, before we had y limits, right? We had x equals 0, x equals a. Then we had y limits, y equals 0, y equals a. But for z, they're infinite, aren't they? And the real truth is, the only thing that can happen is you're going to have propagating solutions. This is a propagating solution. Do y'all follow me? It's e plus or minus j beta z times z. Do y'all follow me? Remember, the e to the plus or minus j beta z was a propagating solution, right, for the electromagnetic field in free space. Do y'all remember that? Same deal here. So that means the functional form for z, and I'll just put it here, will be this. But I didn't give you the value of beta z, and you don't get that by using boundary conditions. Now here's how you get it. You come down here and you see this equation right here, class? Here's how you get beta z. Just listen. I got beta x, right? I got beta y. Those are based on the structure, right? On the dimensions, the cross-sectional dimensions. I have beta u. If I know what frequency I'm putting in, I have omega squared mu epsilon. The mu and epsilon would be of the media I'm traveling on, the interior to that dial or to the waveguide. With me? That means beta z is what? Well, beta z, write this down, is really Wentworth's beta, I'll put that here, is equal to, well, take beta z to the other side, right? It's going to be the square root of beta unguided squared minus the quantity beta x squared plus beta y squared. Y'all follow me what I'm doing here? I just take this equation, I take beta z to the other side, take the square root of what remains, I have beta unguided minus the quantity beta x plus beta y squared. Do y'all follow me on this, class? Now I move over here. And I'll tell you how to get beta z in 1 second, but I want to write this down. That means the actual function of ez, all right, will be equal to some constant, and most of the time they call it E naught. It's a scalar value, doesn't matter. Then it's going to be times the sine of m pi x over a. Then it's going to be times the sine of n pi y over b. Then it's going to be e, and it can be a plus or a minus j beta z times z. That's the functional form ez will have. Do y'all follow me? Now, this dictates if it's a positive or negative going away. If it's minus j beta z times z, then it's positive going. If it's plus j beta z times z, then it's negative going. Now remember that from before, class? I don't want to hit that, spend time on that. So that's the general form of the solution. To get beta z, right, square root of beta unguided, well, beta unguided is omega squared times mu epsilon minus beta x. Well, beta x and beta y were what? M pi over a squared plus n pi over b squared, right? And that is beta sub z. Are you with me, class? I'm trying to show you this methodically, right? I know, a lot's coming at you, and a lot of it you don't see how it's applied to solve the problem yet, but you gotta go through this. Y'all with me at this point? Now, I get down to here, and now a logical question is, so what? I mean, that's, how do you know what M and N is? I mean, what is this gonna tell me? Here's the key thing. We look for what causes cutoff, or what causes beta z to go to 0. This is the key. So why am I saying that? When beta z goes to 0, that tells me that nothing propagates. Y'all hear me on that one? When beta z is 0, nothing propagates. There is no variation with z. Literally, the wave is ricocheting up and down off the bottom of the guide. That's what I'm trying to tell you. Well, that has a peculiar effect on frequency. It says that frequency, if we can find it, is called the cutoff frequency. Y'all hear me on that one? So when beta z equals 0, that means this is 0, right? Y'all hear me? All right, so when beta z is 0, I take a look here. Instead of omega, we put omega cutoff squared times mu epsilon will be equal to, well, now I take this to the other side, will be equal to m pi over a squared plus n pi over b squared. Now the only thing I've done here is I've taken this inner part and set it equal to 0, because if the square root of it equals 0, whatever's inside equals 0. Do you agree with this, class? All right, hang with me here. That's called the cutoff frequency. This is the frequency we're actually after. So when we look at this, what I'm going to do is this. And you don't need to write this next part down. If you listen, it'll make sense, because it'll save you some trouble. You know, omega is what? 2 pi f, isn't it, class? Y'all agree with that? So this is really 2 pi f cutoff squared. Okay? Now, y'all see how there's a pi squared that appears everywhere. Can y'all see that, class? On every side, right? Here, there's a pi squared, pi. So I just get rid of it. Okay? Now remember, that's just geometry right there, right? And I know the integers are gonna bother you, I'll help you with that in a second. But now, what I say is I can look at FC by itself, the cutoff frequency, but this cutoff frequency is gonna be a function of M and N, and I'll get there in a second, will be equal to 1/2, and then it will be square root of mu epsilon times the square root of m over a squared plus the square root of n over b squared. Now the only thing I've done here, I've literally said, well, I know FC is going to be a function of m and n, right? Now I have FC here. These are called the cutoff frequencies. Write that down next to it. These are the cutoff frequencies. For the different modes. Okay, got something important to say now. So, if that's the case, when I look at this, so what? Well, think of what M and N mean. When I look at this function right here, M is an argument here, right? N is an argument here. What happens if both are 0? What happens? What's the sign of 0? You got nothing, right? So there is no mode that's a cutoff for the 0, 0. Do y'all follow me on that? There's no such thing. So what does the 1/0 mode mean? This is the lowest, this cutoff frequency has meaning. If I put 1/0, don't write this down yet, you gotta hear me. If I put 1/0, what does it mean? Well, I would have 1 for M, but I would have 0 for N, right? Wouldn't this still be 0? And here's the point here. With TM modes, the lowest possible mode number would be 1, 1. Both M and N have to be 1 for this to work. And that means the lowest possible frequency, these are for TM modes, would be FC 1, 1. This is the lowest frequency for the TM modes that will propagate. Which happens to be 1/2 square root of mu epsilon, right? And then it's simply square root of 1/a squared plus 1/b squared. And that's it for TM mode. You know what's really nice? We don't use TM mode. Okay, there are some special circumstances. You don't have to worry about it. What we use is TE modes. Y'all see this stuff, what I've done so far? Now, another thing that's going to happen, I didn't want to spend a whole lot of time on this, but if I have beta z, remember, beta z is this right here, right? And how many remember when we have beta, that we can get the velocity? Do you all remember that? For a wave, I can prove this if you want me to, but when I have beta z, right, of a wave that's propagating into the time domain, I'd have to multiply this thing by e to the j omega t, take the real part, right? And I would eventually get a cosine of beta, or of omega t minus beta z, if it's a positive traveling wave, right? Then I could get something called the phase velocity. So write this down. The phase velocity, v phase here, will still be equal to omega, but it will be over beta sub z. This is the phase velocity in the z direction. You all follow me, class? In general, phase velocity is something that has to do with propagation in a certain direction. This is the phase velocity. And I want to tell you, the phase velocity of this wave can go beyond the speed of light, because phase velocity doesn't mean anything about real energy flow. I want to just make mention of this. You all know how waves in the ocean come up and hit the shore. And if they're coming at an angle, assume this is a front, hitting the shore, the point where it intersects the shore has a different velocity than the wave front moving this way. You all see that? And as this wave gets shallower and shallower, when it's moving this way, this point's moving super fast compared to the actual. The phase velocity we talk about here is not the velocity of energy. It can approach infinity, all right? but it doesn't mean anything about energy. Do y'all hear me on this? It's important. Energy is different. It'll never go faster. And the energy flow in a waveguide will always be less than or equal to the speed of light. Less than, significantly less than usual. All right, so that's the TM mode. I got through that. Tried to. I didn't get the. I'll put the solutions for this up on the on OneNote. All right, now give you some homework. We'll go through the TE mode next time. So the logical question is, do we have a quiz on Friday? Answer will be no, but I'd like you all here. All right. If I have to, somehow I'll take attendance for the quiz, and you'll get some crazy points. I want you here though on Friday, okay? Because I need you here.